In a previous video, the one right before this, we introduced maximum likelihood estimation. I defined that and did a couple of examples. And we did this Gaussian example where here was the here was the likelihood function. And we did this little trick. In effect, we took the log of this likelihood function and we kind of switched it from maximize this whole thing to just minimize this sum up here because of the form it takes. So this J became a new cost function, and you could call it a log likelihood, although we're trying to find the minimum, not the max. But that is something we do so much, it has a name. It's called log likelihood. And it happens a fair amount because so many PDFs have involve exponentials and exponents. Well, let's do another example where that happens. Poisson PDF, probability density function. It has this form. In this case, we don't know the parameter lambda. But we're going to want to estimate a lambda based on a bunch of samples of x. We're actually doing experiments where we got a bunch of x's, x sub 1 through x sub k. Log likelihood function was this joint density, this joint PDF, conditional PDF, conditioned on lambda. We assume independence, so that joint PDF becomes this product where each term looks like this guy up here. So here is our likelihood function. But we're going to use log likelihood. So we're going to take, this is a product of terms, right? We're going to take the log of that whole thing, that will become a sum. So each term will take the log of. And here's some algebraic review and a little calculus review, how to deal with logs. And we kind of do it term by term here because it's a product and a division, okay? So for this term here, it's just going to be minus lambda. For this guy here, you bring down the exponent, so it'll be x sub 1, or for any term, it's x sub I times the log of lambda. And then, because we're dividing by x sub 1 factorial, it's minus the log of x sub 1 factorial. That's not going to come into play because what we want to do is take the partial or the derivative of this guy, this log likelihood function or this cost function. And this is, we're finding the maximum of this guy, so maybe I shouldn't call him a cost function. It's just a log likelihood function. And when you take the derivative of this guy up here, you bring the derivative inside, we're taking it sum by sum, and with respect to lambda. So the derivative of this first term is just minus 1. The derivative of this guy with respect to lambda is 1 over lambda times the xi. This guy has no lambda in it, so that derivative is 0. So there we go. You can separate terms, and you're just summing a bunch of 1s up to k. So you're going to get a k equals sum of these terms. Lambda is a constant, so you can bring it outside the sum and solve for lambda. And you get this relationship, which coincidentally is just example mean again. Not guaranteed of it. It just crops up in various examples, but not all. Okay, let's talk about one other thing with maximum likelihood. Here we bring back this measurement equation. Measurements Z have this linear relationship with the state or the thing we're trying to estimate. And it's corrupted by errors. In this case, we know the whole PDF of the errors, not just the first and second order statistics like in the previous example. In fact, it's Gaussian, multivariate Gaussian. So it has this, and we know the covariance. It's a zero mean. We know the covariance R. So the log likelihood, the likelihood function becomes this PDF, this conditional PDF, which is this guy, but we replace the V with what V is. Solve this guy for V, it's just Z minus HX. So put Z minus HX in for V up here. And that's the thing we want to find an X that maximizes this. It's a little bit of a head scratcher. So we want the X that maximizes this guy. We could find that, just like in the log likelihood function. This part doesn't matter. It's just some constant. We have this exponent with a negative up in the exponent. So we want to minimize this part of it. Z minus HX transpose, etc. So we want the X that minimizes this. That is weighted least squares, and we've already found the solution for it. It was this. And it's kind of remarkable. That's the same solution as the Gauss-Markov theorem, where we did not know the PDF of the errors. All we knew was their first and second order statistics. But in that case, we imposed that the answer be unbiased and the estimation relationship be linear. We imposed those in that case. In this case, we get the same answer, but we didn't impose any such conditions. We didn't even say what best was. Actually, in this case, best is maximum likelihood. In the previous case, it was minimum mean square error. That's kind of neat. The next subject is going to be Bayes estimation or maximum a posteriori estimation, and it's kind of an extension of maximum likelihood. But I'll save that for the next video.